In our last video, we set out our next goal as one where we would find a connection between all the tension forces, namely that T1 equals T2 equals T3 equals T4, on and on, which we replace with a single variable T. And we said that we would use assumptions 2, the fact that the pulley was massless and frictionless, to show that T3 equals T4. We further said that we would use assumption 3, the fact that the string is massless, to show that the magnitude of T1 equals the magnitude of T3 and that the magnitude of T2 would equal the magnitude of T4. Now, before we show that our assumptions will result in uniform tension, let's look at why this assumption is not so obvious. To do this, we'll do another thought experiment. And in this thought experiment, we'll consider an extremely heavy pulley, or one with infinite friction. The point is, we don't want the pulley to rotate. We can achieve this effect by placing our finger at the top of the formerly ideal pulley. The large arrow at the top of the diagram is to indicate our finger force. Now, when the pulley is fixed and cannot rotate, the net acceleration of both masses is 0. That is, our net acceleration A is equal to 0 in our system of equations. As a result, we can immediately solve for the tension forces T1 and T2. That is, T1 equals M1 times G, and T2 equals M2 times G. Further, we see that the tensions are not the same. In fact, T1 will be greater than T2 because we've assumed M1 is greater than M2. In this non-ideal case, we have T1 greater than T2. So it's not always correct to assume the tension is uniform everywhere. As we shall see, this only occurs in our very special case of ideal conditions. So let's return to our original analysis and work with assumptions 2, the assumptions that our pulley is massless and frictionless. Now, we need to establish some working definitions and lightly introduce a few new concepts. Now, a massless pulley will have no moment of inertia. Now, a moment of inertia plays the same role in rotation that mass plays in translation. The moment of inertia is a measure of an object's resistance to rotation. Now, I'm going to be guilty of a hand wave. And to be clear, hand waves are legal, but only when they are communicated as such. So, my hand wave is this. I'm going to avoid a mathematical derivation of moments of inertia because the details will not provide much insight into the ideal Atwood machine. That is, in order to be rigorous, we have to define what we mean by an axis of rotation and define what we mean by a moment, which involves an integration. So I'm requesting that we leave our definition as this. The moment of inertia measures an object's resistance to rotation. The larger the moment of inertia, the harder it is to rotate an object. For a pulley, we find the moment of inertia to be equal to 1/2 times the mass of the pulley times the square of its radius. We can confirm this formula by looking in a table of moments found in many engineering texts on dynamics. The implication of a frictionless pulley is that no energy is used by the torques in getting the pulley to rotate. That means tension forces T3 and T4 do not have to overcome any additional forces in order to get our pulley to rotate. And finally, there is a rotational analog to Newton's second law. That is, net torque equals the sum of the torques, which equals the moment of inertia times rotational or angular acceleration. Here we'll use the capital Greek letter tau to represent torque, the letter I to represent the moment of inertia, and the Greek letter alpha to represent angular rotation. Alpha tells us how fast the RPMs, the revolutions per minute, the pulley is changing. The intuition is this: the more torque applied to an object, the greater will be its angular or rotational acceleration. These torques are moderated by the object's resistance to motion, which is captured by I. Now, a torque is defined by the vector cross product of a force applied to the object with its lever arm. The lever arm is simply the distance between where the force is applied to an axis of rotation. For a pulley, the force creating the torque is the tension on the pulley. In our problem, this is T3 and T4. Further, in our problem, the lever arm is equal to the pulley's radius. Now, the magnitude of torque includes a sine term, where the angle theta is the angle between the applied force and the lever arm. In our case, the angle is 90 degrees, and therefore the sine term is equal to sine of 90. Since the sine of 90 degrees is equal to 1, the sine term disappears. Now let's put this information about our torques into Newton's second law for rotation. To do this, we'll need one last piece of information, the sign convention. In our analysis, we'll assume torques producing counterclockwise rotations are positive and torques producing clockwise rotations are negative. So our equation becomes positive torque 3 minus torque 4 is equal to I times alpha. Again, where I is the moment of inertia and alpha is the rotational acceleration. Torque 3 is equal to T3, the tension 3, times the radius r, times sine of 90 degrees, which equals T times r, or T3 times r. Torque 4 is equal to T4 times r times sine 90, which again equals T4 times r. Now, since I is equal to 0 for a massless pulley, we have T3 times r equals T4 times r. Canceling the r terms, we find that T3 equals T4. Hence, we've established that the massless pulley assumption leads us to the conclusion that the tensions are the same on either side of the pulley. Again, the important intuition to keep in mind is that this is true only in our special ideal case. Ordinarily, to get a pulley to rotate, one torque must be greater than the other. That is, to rotate counterclockwise, torque 3 must be greater than torque 4, which means tension 3 must be greater than tension 4. Because in the ideal case we have no moment, the tensions on both sides of the pulleys are equal. So lastly, we'll find out what the implication of a massless string is. But to reinforce the intuition behind the physics of the problem, I want to examine the opposite case, the heavy string. So let's assume we have a small piece of string attached to a ceiling beam and that the string has weight capital M sub s. We can create a force body diagram for the small piece of string and immediately identify two forces. There is T5, which is the tension force of the ceiling on the small string, and the weight of the string, which is capital M sub s times G. Now I'm adding a third tension force, T6, which I'm defining as the tension force applied to the bottom of the string. Now, since there is nothing pulling on the bottom of the string, T6 is 0. I've added T6 to reinforce the idea that the tension in the string starts at 0. Now, using Newton's second law and our force diagram and our up is positive sign convention, we can write positive T5 minus T6 minus capital M sub s times G equals positive M sub s times A. Now, since this is a static problem, the string is not moving. Therefore, A equals 0. This means that the term on the right goes away. Since T6 is also 0, we have that T5 equals ms times G. And in fact, we solved this same problem in an earlier video. Now, if we assume the piece of string is uniform, that is, its mass is uniformly distributed, we find the tension increases steadily as we move up the string. That is, the tension starts at 0 on the bottom and increases to the weight of the string at the top. The intuition is this: the self-weight of the string adds tension. Now, let's conduct a similar thought experiment with a section from the middle of our ideal string. For a moment, let's think about this section in isolation. From the free body diagram, we can identify three forces acting on our isolated middle section of string. T7 is the tension on our section from the string above our section. These forces will tend to pull our section of string up. T8 is the tension on our section from all the string below our section. These forces will tend to pull our section down. The third force is the self-weight of the section and equals m sub s times g and points down. Now the sign of the net acceleration depends on which side of the pulley our section resides. That is, A may be in an upwards or downwards direction. I've indicated this with double red arrow in the free body diagram. Now, for our problem, I've assumed the net acceleration is positive. In fact, ms equals 0. Therefore, the sign becomes irrelevant. Now, plugging all our force data into Newton's second law, we have T7 minus T8 minus ms times g equals positive ms times a. Now, when ms equals 0, two terms drop out, and we find that T7 equals T8. That is, the tension is the same at the top and bottom of the string. In fact, the tension is the same throughout the string. By repeating this argument, we can make our string any length we want by adding small sections to it. And we'll find that the tension is the same throughout our string. In this way, we can conclude that the magnitude of T1 equals the magnitude of T3, and the magnitude of T2 equals the magnitude of T4. Now, we're almost at the end of our analysis. To recap, we found that T3 equals T4 by using our ideal assumption of a massless pulley. Furthermore, we found that the magnitudes of the tension are uniform on each side of the pulley by using our ideal assumption of a massless string. That is, the magnitude of T1 equals the magnitude of T3, and the magnitude of T2 equals the magnitude of T4. Now, finally, we can combine both conclusions and show that the magnitude of T1 equals the magnitude of T3 equals the magnitude of T4, which equals the magnitude of T2. And we can replace all these tensions with a single tension, which we'll call T. Now, by replacing T1 and T2 in our earlier system of equations, all the way from video 1, we now have two equations and two unknowns. This was a journey, but I hope you now have a deeper understanding for the underlying physics behind the ideal Atwood's machine. It is not a trivial problem after all. In the next video, we'll solve for the acceleration and tension and see what our answers tell us about the dynamics of this system.